Good morning and welcome to today's discussion. Today we want to take some real life examples under ARMA 1-1 models. In our previous class, we looked at ARMA models in general. We now concentrated our discussion on ARMA 1-1. And in that ARMA 1-1 model, we looked at how to write the model number 1. We looked at how to drive the mean of the model number 2. We looked at how to drive the variance of the model number 3, and we equally looked at how to drive the autocorrelation function of the model. Today we just have a simple example that is drawn around ARMA 1-1, and we are asked to make some computations. So we read the question with you. The question says, for ARMA 1-1 model, mu is given as 2, phi 1 is given as 0.6, theta 1 is given as 0.4, and sigma squared A is given as 1, 9. Is given as 9. And the question says, compute A, the mean of the model, that is the mean of ARMA 1-1 model, the variance of ARMA 1-1 model, and the autocovariance function at lag 1 of ARMA 1-1 model. So we are going to make use of the formula already derived from our previous class when we discussed ARMA 1-1 model. So we refer you to the class in case you begin to find the formulas we are going to write a bit challenging. So we have a solution. We are going to begin from the mean of ARMA 1-1 model. In our previous class, we gave the model of ARMA 1-1 model to be that y of t is equals. We had phi 0 plus. We had phi 1 y of t minus 1. We had what? A of t, and we had what? Theta 1 a of t minus 1, where our a of t follows a normal distribution with mean 0 and variance sigma squared of what? A. This is the model of ARMA 1-1 model. Now what we are going to do now is to use this model and then match the values that we are giving to us this place. We are seeing phi 1 here, and phi 1 is given to us as 0.6. So under this solution for the mean, first of all, I will now say givens. My phi 1 is given as 0.6, and here is our phi 1. Our theta 1 is given as 0.4, and this is our theta 1. So theta 1 is equal to 0.4. Then we are given what? Sigma squared of A. Look at our sigma squared of A here, which is the variance of the error term. So sigma squared of what? A is equals to what? 9. Now, the only thing we cannot find here is what is called the theta phi 0, which of course is the constant of the model. But we are given that mu is equals to what? 2. So oftentimes they use different notations to represent the constant of what? Of the model. In the model we gave here, the constant of the model is the phi 0. But in the question posed to us, they are looking at the constant to be what? To be 2. So I have that now, these are constant now, which is now phi 0. It's given as what? Mu, which is given as what? 2. And we derived the mean of the model from our previous class to be that the mean, which is what? Mu of y of ARMA 1-1 model, is given as phi naught all over 1 minus what? Phi 1. This is the value that we derived in our previous class. So we now quickly say this implies in the place of what? Phi 0, I am going to write 2. So I have 2 all over. Here becomes what? 1 minus. My phi 1 is given to me as 0.6, so this becomes 0.6. If you evaluate this, the value is given as 5. So we have been able to find the mean of ARMA 1-1 model. So we quickly look at the variance of ARMA 1-1 model, which is not, this is number A, this is number B. The variance of ARMA 1-1 model is given as var of y of t, which is the same thing as sigma squared of what of y, which is equals. We had it to be what? 1 plus. We had what? Theta 1 all squared plus 2 of phi 1 theta 1 close the bracket all over 1 minus phi 1 all squared multiplied by sigma squared of what? Of A. So this is a formula of the variance of ARMA 1-1 model that we already derived in our previous class. So you can make reference to the class to see how the variance of ARMA 1-1 model is derived from this model. So what we are going to do is to quickly substitute into this our model now in order to find the value of our variance. So here we have that this equals, I open a bracket, here becomes 1 the way it is plus. My theta is given as what? 0.4. So I have 0.4 all raised to power 2 plus. Here is my 2. So I have 2 multiplied by. My phi 1 is given as 0.6. So this is 0.6 multiplied by. My theta 1 is given as a 0. What? 0.4. So I have what? 0.4. Close the bracket all over. Here is my 1 minus. Here is my phi 1 and phi 1 is given as a 0.6. So I have a 0.6 all raised to power what? 2. Multiplied by what? 9. Because sigma squared of A is what? 9. And if you evaluate this, which I have on the board, the value is given as 23 points. It's given as 23.0625. So this is then the variance of the ARMA 1-1 model. Permit me to bring my curtain down to prevent the reflection of light coming inside the class. So we now quickly look at the autocovariance of ARMA 1-1 model at lag 1. We already derived the formula for this autocovariance in our previous class. And then the formula we derived is given as, which is number C. That number C is given as gamma 1. Gamma 1 stands for autocovariance function at lag 1. We had it to be that this is given as phi 1 gamma 0 plus what? Theta sigma squared of what? Of A. This is the formula that we already derived in our previous class. So we are going to make use of this formula now in order to obtain the numerical value of the autocovariance function at lag 1 of ARMA 1-1 model. Gamma 0, another name of gamma 0 is variance. And we already computed the variance. And then we are giving phi 1 to be 0.6. We are giving theta 1. And then we are giving sigma squared of what? Of A. It's just to make a quick substitution here. So it implies that this thing will now be 0.6, which is what I have here. Open a bracket. My gamma 0 is same thing as variance. So I have 23.0625, close it, plus. Here is my theta 1, which is 0.4. So I have 0.4 multiplied by what? 9. Since sigma squared of A is given as what? 9. This is the value of the autocovariance function at lag 1. And if you evaluate this, the value is given as 17.4375. Yes, we have got all the values required of us to obtain from this question given to us on ARMA 1-1 model. Another concern becomes, how do we interpret these results which you have got from this question? The variance of the the mean of the model is given as 5. So the implication is that the value of the series fluctuates around a constant mean 5. That is the implication. If you plot the values of the series or you plot the value of the data, you find out that the value of the data will be fluctuating around this value 5. That is the implication. So if you simulate a observation of this ARMA 1 model, making use of these parameters given to us, and you plot this simulated value, you are going to find out that your graph is going to show values that fluctuate around this constant value 5, which is the mean of the model. That is the interpretation there. Then the next thing becomes what? Variance. How do we explain the variance of a 23.0625 with relation to this ARMA 1 model? Of course, we know that variance is the measure of the deviation of the observation from the mean of the data or from the mean of the model. And then seeing this value 23 point something, we can see that there is a high fluctuation of the series from its mean 5. The mean is 5, but then the variance is what? 23 point something. So the gap is quite much and the fluctuation is quite much. And such interpretation is time series is to quickly say that that model exhibits what is called volatility. It has a high volatile behavior, fluctuation from the mean of what of the model. That is what we can say about that. Of course, you know that if you take the square root of this variance, if you take the square root of this variance in order to obtain what is called a standard deviation, you now will be talking about the sigma of y. If you talk about that, you have that sigma of what? Of y will be given as square root of 23.0625. And then the value of this standard deviation will give us something as 4.8 approximately. It will give us a 4.8 approximately. 4.8 approximately. So the implication is that you are going to see that the value is going to fluctuate around 5, which is the mean. Here is the mean, then plus minus this standard deviation, which is 4.8. Don't you see that if you subtract this 4.8 from this, you'll be able to have about 0.2, and when you add this thing, you'll be able to have about 9.8. You see how the values can throw as small as up to 0.2 and as large as 9.8. Moreover, the mean is just 5. So the fluctuation is quite what much. That is the interpretation we can give to variance, which is equal to the interpretation we can elicit from the standard deviation. Then we quickly come and look at now the autocovariance. How do we explain the autocovariance? When you are talking about autocovariance, you are trying to measure the extent of the dependence of the current observation of the series on its past value at lag 1, because we are discussing lag 1. And we are seeing the value here, 17.4375, showing us a very high dependence of the current observation now on its previous observation at lag 1. That is how we can talk about this. And we can equally see this thing because when you talk about what AR now measures, or we say that AR now is a model that tells us now how the current observation now depends on its previous value. And we are seeing that the parameter of AR here is 0.6, which is still pointing at the high dependence of the model on its previous values. So this is how to make interpretation about this. Let us now quickly now look at now what we call the condition of stationarity of ARMA 1 model. We want to make it clear here that before you can apply ARMA 1 model, one of the assumptions that must have to be satisfied is stationarity condition. When we are given the ARMA 1 model, how do we say, on which condition or basis do we say that that model is stationary? Let me quickly clean this and explain quickly for you. The stationarity condition of ARMA 1 model depends on the parameter of the AR of order 1 model that is in it. Because ARMA 1 model is the combination of AR of order 1 and MA of order 1. And AR of order 1 has a parameter, and that parameter is called phi. And that phi is given to us as what? 0.6. And we are saying that the stationarity condition of ARMA 1 model depends on the parameter of the AR model, not on the parameter of MA model. And that parameter of the AR model is given as a 0.6. And that condition is that absolute value of what? Phi 1 must be less than what? Must be less than what? 1. That is the condition of the stationarity of the ARMA 1 model. So when we are given any ARMA 1 model and this condition is satisfied, we can go ahead and say that that parameter, model is stationary. Okay? So where we say that this is less than 1. However, when we say that absolute value of a phi 1 is approximately 1, we are saying that the model is approaching non-stationarity condition. But when we have the absolute value of a phi 1 is greater than what? 1, we quickly say that the model is not stationary. So look at these three conditions. The first one says the model is stationary. This one says the model is approaching non-stationarity condition. And then this condition is saying that the model now is non-stationary. We are saying this when we have a model at hand. Okay? What is now going to happen to us? So looking at this question, the phi 1 is 0.6. And of course, the absolute value of phi 1 is less than 1. So we can say that this ARMA 1 model given to us in this question is stationary. What if now we are not talking about model, we are talking about real data? If we are talking about real data now and we want to assess the stationarity condition of ARMA 1 model, you are going to do it now in three conditions. One, you are going to look at the visual graphical values of this ARMA 1. And how to look at it graphically or visually is, number one, from a real data. You look at it what? Visually. And then in this visually, you are first of all going to plot the values of a ARMA 1 model or data of a ARMA 1 model. And you check, number one, whether it has a constant mean. Number one, whether it has a constant mean. And number two, whether it has a constant variance. If it has a constant mean and a constant variance from the graph, you quickly begin to suspect the stationarity condition of that data which you have at hand. And then you can talk about what we call the constant autocovariance. So these are the conditions that you look at now from your graph for us to begin to suspect the stationarity condition of that model. Now, graphically, it is not enough for us to conclude the stationarity. So we equally talk about other ways that we can begin to assess our stationarity conditions using the plot of what we call ACF, autocorrelation function, ACF. When we plot the ACF of ARMA 1 and we obtain the following, that this ACF of ARMA 1 decays quickly. It decays quickly. We begin to suspect that the model is stationary. But when this ACF now decays slowly, when it decays slowly, near the value 1 or near 1, we now suspect that the model is not stationary. For us to conclusively conclude on the stationarity condition, after plotting the graph of the original data, seeing constant variance, seeing constant mean, seeing constant variance, and seeing constant autocovariance. Okay? We have equally gone ahead now to have a plot of our ACF. And we have now seen that the graph decays quickly. We are going to go ahead to conduct another test, which we call the root mean test, for us now to conclude now whether the thing is stationary or not. And then we are going to use a test called augmented decafla test. Okay, for us ADF, or augmented decafla, ADF. We now go and conduct ADF tests. Okay, and then in this ADF test now, you are saying that the root of the equation of ARMA 1-1 model lies within a unit circle. Okay, and then against that, it did not lie within a unit circle. So once you conduct the test now, you will be able now to categorically now know exactly now whether your model is stationary or not. Thank you very much. We have just done one real life examples of a question on ARMA 1-1 model. Still stay connected. Other classes will be coming your way from these complex time series models.